Hello. Hi, everyone. My name is Agnieszka Potulska. I work at Intel, at DCG Intel, which stands for Data Science Group, Datacenter Group. First of all, I would like to thank you all for being here, even though it's 5 p.m. Friday, but you are still here with us, so we are pretty happy about this. So we are going to speak with Piotr Tylenda, also from Intel, about log analytics in data center with Apache Spark and machine learning. When it comes to the agenda, at the beginning, we will define what business problem and what's the pipeline that we deployed in order to solve this problem. Next, we will move on to some machine learning algorithms and techniques that we used in our pipeline. And in the end, we'll show you the results, as well as discuss some conclusions and lessons learned from developing this solution. So, at the beginning, I would like to say that we work in DCG, Datacenter Group, which means that basically our main point of focus is to analyze and collect the data that is coming from the data center. Basically, as a workload here, we will describe the defined set of actions that are going to be executed on the specified server at a given time. Logs from these workloads contain a lot of information about the operating systems that are installed on the servers, about the network traffic, about the user's behavior, or even about the software stack that is installed on the particular servers. And because of the distributed nature of these systems, of data centers, as well as because of the fact that they are of very large scale, sometimes it may happen that engineers are working independently to troubleshoot the same issues without knowing that the solution is already there or that someone is already trying to figure out how to fix the similar or even the same issue. And in order to avoid this possibility of the application of work, we proposed a machine learning workflow. Basically, the idea is to set up a pipeline that will enable engineers that are usually troubleshooting the issues within a data center to detect these similarities, the similar problems, issues, at an early stage, without the need to go to and analyze each logs one by one. And it's very worth mentioning at this point that very often there are tens of millions of these messages. So the whole point here was to set up a pipeline and collect logs from different sources that I mentioned on the previous slide, and collect them in one place and apply some machine learning techniques, such as, for example, clustering. In order to accomplish this, we developed this pipeline. This is the very high-level architectural overview of our pipeline. As a starting point, we have here a metadata store and a workload scheduler. In metadata store, we have information about what's the name of the workload, what are the steps of the workload, what machines are being used within this workload, and what's the time of execution, and so on. After that, the workloads are being executed on the clusters. Clusters are basically geographically distributed. Machines are placed in different countries, even on different continents. And each from the nodes of this cluster publishes the messages into Kafka. Kafka is a distributed publish-subscribe bus, event bus, and serves as a data store for Spark streaming and Logstash. With the use of Spark streaming, we transform the data into HDFS for further analysis and Spark machine learning algorithms. And with the use of Logstash, we ETL, we load the data into Elasticsearch and Kibana. And now I will explain into a little more details what were the reasons that we chose this particular components and not the other ones. Kafka, as already other presenters mentioned, is very convenient for having different producers that produce the data in different formats from different places. And I already said that that's the case in our pipeline. And also, it enables real-time processing and real-time event sourcing, which is very crucial when it comes to data center and troubleshooting the issues in data centers. Apache Spark streaming, we are using it for processing the data into HDFS in micro batches. ELK stack. We decided to have 2 pipelines and use also Elasticsearch stack because of the fact that it provides very convenient, very nice features for full text search. And we found that it was better for us to use Elasticsearch for full text search than to implement it on our own with the use of Spark. Apache Spark is the component in which we implemented some machine learning algorithms, and Apache Zeppelin is the web-based notebook for data scientists. It's kind of similar equivalent to Jupyter. And speaking of data science, machine learning, I mentioned at the beginning that we would like to discover the similar workloads, failures, by clustering the logs. And basically, these logs are texts. They are not plain English like Harry Potter or The Lord of the Rings, but still they consist of words and they convey meaning. That's why we decided to use text mining approach and use text mining algorithm applied to text. Basically, the objective of clustering is to group objects into sets of similar objects. Similarity is kind of vague term because it can be expressed in different ways. There are different similarity measures. We'll cover this on the next slides. And this technique is widely used in exploratory data mining, and this is an unsupervised machine learning technique. Here we have an example of particularly Kmeans algorithm, the one that we are using in our pipeline, applied to S1 dataset. S1 dataset is very common dataset in data science. It consists of an artificial data of 5,000 vectors on 2-dimensional space. Here the attribution to clusters is based on the color, so red points are the members of the one clusters, and blue points are the members of the second cluster. And the similarity here is computed based on the 2-dimensional Euclidean distance, which means that basically that's the length of the vectors on a 2-dimensional space. When it comes to clustering in general, it is worth mentioning that there are multiple families of clustering algorithms. First family is hierarchical clustering. The main aim, the main point here is to build up a hierarchy of clusters, and the results are usually presented in a dendrogram, an example of which you can see on this slide. Next family is a density-based clustering. Basically, clusters are considered to be the places of higher density than the remainder of the data set. And the most popular algorithm within this group is a DB-scan algorithm. Third group is a distribution-based clustering. That's the group more related to statistics, distribution, and so on. And the last one is the approach that we are using. It is called centroid-based algorithm because of the fact that clusters are defined as a points that are the closest to the center, the centroid of the cluster. And basically, the representation of this family, this type, is Kmeans algorithm. OK, so when it comes to Kmeans, I mentioned, you saw also on this graph, that Kmeans algorithm works on vectors. But before we have a vector, there are certain steps that need to be performed for a text, because we are dealing with text. So first step is to filter the data, filter the text. We would like to discover the similarity between the failures. But we also have log messages that are of level info, debug, warn, and so on. So as a first step, we filter the failure messages from the other ones. Next, we perform stop words removal and tokenization, which is kind of a data cleansing. So we split the text into terms, into words for further analysis. Next, we perform feature extraction. That's the place in which we will have vectors afterwards. There are multiple ways to perform feature extraction for text. And the most common one, the most popular ones, are TFIDF or word-to-vector conversion. And I will explain this on the next slides. Next, we can normalize our data, as a result of which we will end up with spherical K-means, because this way we will map our data points to the unit sphere. But this is an optional step. No need to perform this. And at the end, we will have our proper machine learning Kmeans algorithm. So, feature vectorization. The question is how to represent text as vectors. It is possible because of the fact that there is a model for that called vector space model. And this model assumes that each text can be represented as a vector, of which each dimension corresponds to a word in this text. So here you have a very artificial, very simple example. We have two documents, and document number 2 can be represented as a vector 19032. 0 means that this particular word appears in the vocabulary, so appears across the corpus, but doesn't appear in this particular document. There are, of course, more sophisticated, more convenient ways of representing text as vectors. And the next one is TFIDF, which stands for term frequency inverse document frequency. That's the most popular one, actually, in data mining. It is also used widely in search or in text mining. And basically, the main advantage of this approach is that the weights that we are adding to the vectors, to the frequency vectors, correspond to the meaning, to the relevance of the words. So here you can see on this formula that this is basically a product of term frequency, which is the thing that I mentioned on the previous slide, and inverse document frequency. Inverse document frequency is the weight that we compute based on the document frequency, but the more documents the word appears in, the lower this value is. And let me demonstrate this on a very, very simple example. Here we have two documents, basically phrases. One is, I like red. The second one is, I do not like red. So when computing simply term frequencies, we'll end up with a bunch of ones and zeros. That's OK. Then we compute IDF, inverse document frequency. Log for 3 by 3 is basically 0. And we multiply each column. And we end up with a bunch of zeros and values. Only two values greater than zeros are for words do and not. And this is good, because these two words are the ones that differentiate these phrases one from another. Words like red appear across the whole corpus, and they do not convey any meaning here in this artificial example. Even more sophisticated method of representing words as vectors is called word-to-vector. This is basically the real machine learning, as opposed to the previous ones, because there are basically some statistics around the term frequencies. But here, there is some neural network behind this involved. This algorithm was developed at Google a few years ago. And basically, with this method, it learns the meaning of the words by learning the context in which these words appear. So on this short example, we can see that basically words like banana, apple, and orange are more likely to appear in one document and in the same context than, for example, words apple and bicycle, which is kind of straightforward. And that's why these words, these points, are closer to each other than the other ones. The thing is that word-to-vec implementation in SparkLib supports cosine distance as a similarity measure. I mentioned before that Euclidean distance is the simplest distance measure that we can use. And it makes it a better fit for Spark machine learning implementation. And that's why we chose it. And next thing is that it provides dimensionality reduction, which makes it more suitable for Spark K-means implementation. And now Piotr will tell you about this Kmeans algorithm.
Okay, thank you, Agnieszka. So let's dive into a bit more details concerning the Kmeans algorithm itself. First of all, this algorithm is a so-called partitional clustering algorithm, which means that it aims at clustering of the data set into a set of disjoint groups, so-called clusters. In this case, in case of Kmeans algorithm, we are clustering the data set into K groups, so this is the only parameter that is required for running Kmeans algorithm. And it's worth mentioning that at the same time, this is the biggest limitation of this algorithm, that you have to choose this parameter beforehand. The key concept in Kmeans algorithm is centroid, and centroid is defined as an average or mean point of all points belonging to one cluster or group. In this picture, it is shown as squares, where, for example, blue square represents an average point of all blue points. K-means at the same time defines a whole bigger family of algorithms based on K-means algorithm. They work at simple principle or similar principle to original K-means algorithm, but they, for example, differ by the definition of how the centroid is chosen or computed. For example, in case of K-medians or K-medoids, it's chosen not as a simple average, but for example, as a median point or a central point in given cluster. And for example, in case of C-means, we are talking about fuzzy clustering, where one point can belong to more than one cluster. And in order to define the algorithm itself, we have to discuss for a while what problem it solves, so-called K-means problem. So this problem is defined that when we are given a data set of n objects we would like to cluster, and this data set consists of d-dimensional vectors, so those are real vectors. We define this problem as we would like to divide this data set into K groups, so-called clusters, in such a way that the following indicator is minimized, and this indicator is called within set sum of squares, which can be seen that it is minimized when the distance between each point and its nearest centroid is the lowest. So it can be seen intuitively that this value will be minimum when the clusters do not have any outliers and they are well defined. So those are small clusters and without any points that are far away from the center. It's worth mentioning that this problem is NP-hard, which means that it is computationally hard, and in order to solve it, there is a heuristic solution which was proposed, and this was the Kmeans algorithm. This algorithm begins by initialization step, which is very important, and we'll discuss it in the next slides. In this case, we are discussing a very simple way of initializing, which is called so-called random method. We are dividing the data set into k-random exclusive groups. So basically, we are choosing a label for each point from 1 to k. And this gives our very initial clustering of the data. And after that, we can proceed with the iteration of Kmeans algorithm, which consists of 2 steps. First of all, we are computing the L2 norm centroid. So in this definition, it's an average point using Euclidean distances. And the next step is to assign, for each object, assign its closest centroid, which will determine the assignment to the group. As you can see, this is an iterative approach, which will update the position of centroid, change the assignment of groups, and again, the groups have changed, so the position of the centroid will change. And the whole algorithm will proceed until some point when there is no change in assignment to the groups in the whole data set. And then we are assuming that the algorithm has been finished. So let's demonstrate it on a real-life 2D points data set. We'll be clustering this data set into 4 clusters, so the k is 4, and Euclidean distance will be used as the similarity measure. So Euclidean distance is basically the distance between the points on this display. And first of all, we are beginning by initialization of the algorithm. In this case, we are using so-called 4G method. It's a bit different method of initialization than we have discussed before. This method is also simple. We are choosing k points randomly from the whole data set, and we are treating them as initial centers. Those are not centroids yet, because this is not an average point of anything in the data set. And after that, we can determine the first assignment to groups using those centers. So this will be the first assignment after the initialization. And now we can proceed with the iteration of Kmeans algorithm itself. So first of all, we are computing the positions of centroids for current groups. As you have seen, those centroids or centers have become now centroids, and they have moved a bit. And after that, we can assign the points to the closest centroids again. And as you can see, those centroids start to move towards some positions that will become their final ones. And in further steps, there are less and less points that change their assignment. So those points that have changed the assignment between groups are shown in red circles. And finally, we arrive at a step when there's only 1 point that have changed, and this is probably the last iteration. And yes, this is the last iteration of the whole algorithm. This is our output clustering for k equal 4. So now let's go back for a while to the initialization itself. It's worth mentioning that it is the most important part of Kmeans algorithm. This is due to the fact that Kmeans is a heuristic algorithm and has so-called gradient descent nature. So it means that if we initialize the algorithm well, it will converge to a good solution. And if we fail at initialization and choose the initial, for example, initial centers poorly, then we can expect that the output clustering will be far from optimal. And as we have previously discussed, we have discussed the random method and 4G method. Those are so-called, or maybe they belong to a family of simple approaches, but people have observed that proper initialization of the algorithm can lead to much better results, so they started to discover new methods of initializing. And the most notable methods are Kmeans++ and Kmeans parallel. Kmeans parallel is a parallelized version of Kmeans++. And this is a probabilistic method. It uses a given probability in order to initialize the algorithm in a much more cluster or dataset aware way. So in the upper picture, we can see the centers that were chosen using the 4G method. As you can see, this simple method of choosing just k points randomly from the whole dataset is not working very well because this dataset, so this is S4 dataset, has about 15 clusters in it, and we would like to discover them. So you can see that the initial positions of those centers are far from anything which is close to centers of the real clusters you are seeing in this picture. And in the lower image, you can see initialization output of Kmeans++ algorithm. As you can see, those green points are placed far better compared to the upper image. And it's worth mentioning that it's only an initialization step. So after that, we are performing the actual iterations of Kmeans algorithm. And this algorithm works in the following way. First of all, we are choosing one point from the whole data set as the first center. After that, each center is chosen depending on the positions of the previously chosen centers. So it chooses one new center in each iteration in a process called d-squared weighting. And this process chooses next center from the whole data set using this probability. And this probability is maximum when a given point is far away from already chosen centers. So it is intuitive that it will try to choose centers from areas that are not already covered by previous centers. And we repeat this step until we have case centers chosen. And now an example code in PySpark, which summarizes all the information we have provided in previous slides. This is so-called Spark pipeline, which consists of several stages. In our case, this pipeline consists of 4 stages. The first one is tokenization. As Agnieszka mentioned before, the documents have to be split into single words. In this case, we are using a white space separation pattern, which is enough for our use. And after that, the next stage is stopwords removal. So we are basically removing all the words which are do not convey any meaning for us that is meaningful when clustering logs. And after that, we have step which consists of word2vec, where when we are performing feature vectorization, at the same time we are reducing the size of vectors, or the size of the vectors, to only 100, so it's much less than the size of the whole corpus of words. And lastly, we are running Kmeans algorithm using Kmeans parallel initialization, the one we have discussed in previous slides, the parallel version. And after the algorithm has been run, or the whole pipeline has been run, we can access any interesting properties for us, for example, the centroid positions, if they are required, or for example, access the within set sum of squared errors, which is a so-called internal clustering validation index. And this index can be used for choosing the k parameter in our algorithm. Because, as I mentioned before, you have to choose this parameter before you actually run the algorithm. So this indicator within set sum of squared errors has one property which makes it, or in other words, it's decreasing when the number of cluster increases. So it's not very wise to just choose the minimum version of K for which it gives the lowest value, because, for example, for a data set with 1,000 documents and clustering it into 500 clusters, you would receive very small values of this indicator, but this clustering is not very fortunate because it doesn't make sense to cluster in such a big number of clusters for such a data set. So there's another method proposed. It's so-called elbow method, and it can be summarized that we are choosing the point where the point in the plot of the value where the plot starts to decrease less rapidly. So this would be about here, because as you can see, this line is much less steep. So probably this would be about 12. And this will give us, using parameter k equal 12, will give probably the best clustering for this data set. And it's worth mentioning that visualization is a very important step in any data pipeline which involves clustering. This is because in most cases you could, for example, display the clustering result as, for example, a table, but it does not give sometimes enough insight into the data. We have created a front end which is based on D3.js framework. And in this visualization, such big circle represents a single cluster of data. And each smaller circle, the colorful ones, represent documents. And we also represent by sizes of those circles how far away from the center of the cluster a given document is. So it gives us, for example, some insight whether we have some outliers in a cluster. So this is another dimension of analysis. And colors are also used for grouping documents that are away from the center of cluster in similar range. So they are very likely to be similar. So for example, when we look at this cluster, this is cluster number 1 in our case, you can see that there are about 250 documents that were grouped together, and they are probably very similar. And for example, we have discovered that those logs come from about 49 machines which have outputted similar kinds of errors, but they will, in standard workflow, they would have to be analyzed by owners of the machines, whereas in this case there is only one engineer needed who can immediately report that some problems have been observed on many machines that are very similar. So it really enhances the process of analysis logs coming from multiple servers. And the last thing is the lessons learned. First of all, what we have observed is that clustering or log analysis requires good consistency in your logging strategy. You cannot allow logging, for example, debug messages as errors or critical messages as warnings. It will destroy the whole pipeline and influence the results significantly. The second thing is that Spark ML implementation of Kmeans supports only Euclidean distance. And this is a limitation of this implementation because for example, the most commonly advised solution for text clustering is using TFIDF and then using cosine similarity. And this cannot be performed in Spark ML right now unless you write your own implementation of Kmeans. You basically cannot write your own implementation of distance and provide it to the Spark ML Kmeans algorithm. And last thing is that we also have observed that document clustering relies on the quality of how you preprocess the data, so how you remove any stop words or not meaningful words. Because it's also connected with the consistency of logging and overall process of preparation of the data. And this concludes our presentation. Thank you. Any questions?
You have shown some figures on the amount of logs that have been processed. Can you share with us how much time it took to build a model? And
this
what
model?
Resources you used?
You mean this in this slide? Yeah, it's about not more than 20 minutes with determining what is the proper value of k. So it was multiple runs for different values of k. We have chosen the right value, which is 56, and the whole process of determining the k and running the final clustering was about 20-25 minutes or so.
Okay, thank you. And one more short question: when you deploy the model or serve the model, what kind of pipeline do you use there?
What do you mean exactly?
I mean, do you run this on actual incoming logs afterwards? So when you
basically we are applying kind of batch processing because that's because of the how our engineers and how our data centers work and where we apply this analysis. But basically we are collecting the data each night and we perform analysis for this particular data at the beginning of the day. If that answers your question.
Yeah, one more thing that's just jumped in my mind. So afterwards, you could actually use predictions. You could predict if certain things happen, certain other worse things will happen afterwards.
Kind of
the next
step, but we didn't deploy it yet, so we didn't include in our presentation. But you're right. Any more questions?
Yeah, there are more questions. One, two. First of all, you gave a very solid presentation, so congratulations. When it comes to the presentation, I saw some keywords like orange, bicycle, Apple, and so on. And I believe that in your analysis, you didn't have such an output, maybe Apple, MacBook, or something like this. I wonder from the business perspective, what kind of scenarios, what kind of use cases you had, what you've checked for this analysis for the data center logs.
Basically, that's the thing that I mentioned at the beginning. We had logs like from operating systems logs, like software logs, because on the servers we have a certain software stack that is pretty well defined. Also network traffic and so on. And as well, we had some sensors data. So basically, we cannot disclose the actual content of these logs, but these are, let's say, infrastructure logs in general.
Yes, this is clear. These are the data sources, but what you were looking for? What were the scenarios? What was the value from this analysis?
We are looking for, because in the data center it happens that, for example, you observe that certain machines rebooted or crashed or something unusual happened. And it requires further investigations. So engineers have to log into the machine, log into the server, and investigate what happened. And sometimes it happens that there are kinds of similar issues. It's not so easy to see when you have like millions of messages and thousands of logs. So we wanted to use Kmeans clustering in order to detect at a very early stage that, okay, these and these machines had probably similar issue. So maybe why not to work on the same problem and not to split. And I also mentioned that these clusters are geographically distributed. And that's the next point here. So we can have, let's say, a log failure management system. Let's put it this way.
Okay, more or less clear. Thanks a lot.
If you allow one more question and then hand over. So basically what you're doing is labeling, right? More or less. Like you are basically categorizing or labeling the logs.
That's the pre-work for labeling, because we discover clusters. Afterwards, experts like the system administrators can put labels, but that's the classification. Like, you know, that's kind of a different machine learning problem. Unsupervised learning versus supervised learning.
Yeah, so this would be exactly the next step we have mentioned in previous questions. Yeah, so first we would be, running the clustering, getting an expert to look at those clusters and determine what happens. For example, an engineer that knows this given part of logs, assign labels, and then you can use it for classification. That's basically the question.
So, I will have next question. So when it comes to collecting the logs and collaborating with the IT system administrators per specific domain, have you collected the logs only from your data centers, or are you collecting also the logs from cloud environments?
Well, not AWS or Azure, because those are only internal.
Right.
For example, we have internal deployments of OpenStack or such things, but those are only internal. So.
Okay, so to sum up, your work supporting IT operations to have a better problem management, to a much faster finding the root causes of some issues, right?
Yes,
in some way, yes.
Thanks a lot. Mr. Balash, do you want to add something? Okay.
Okay, thank you.
From my side, that's all. Okay, thanks.
Okay, so thank you.
Thank you.